We can start. Dear rock mechanics colleagues, thank you very much for being here today and welcome to the first ISRM European Rock Mechanics debate. I am Leandro Alejano and I am the ISRM VP for Europe. Based on an initiative by Charlie Li, this debate and hopefully future ones aim at stimulating communications among academics and practitioners of rock mechanics and rock engineering in Europe. An organizing committee formed by Philippe Vaskou, who will moderate this session, Charlie Li and myself have organized this fair debate on the topic hydraulic fracturing to measure in situ stresses. We hope not to have technical problems, but we apologize in advance just in case. And I inform you that this meeting will be recorded and that it can be followed in an ISRM YouTube channel recently launched, mentioned in the flyer, and that I will include in the chat in a few minutes. So with this, I invite our moderator, Philippe Vaskou, to introduce in more detail the topic of the debate and our speakers today. So please, Philippe.
Thank you, Leandro. So I'm Philippe Vaskou from France. So today for this very first ISRM Euroc debate, we will have two speakers. One speaker from Germany, Gert Klee, and one speaker from Norway, Arne Marius Rein. So each speaker will have 15 minutes, and then we will have about 30 minutes for questions and discussions. So I introduce now the first speaker, Gert Klee. Gert Klee is currently the manager of Messi, now Messi Sol Experts, a company located in Germany. Founded by Professor Fritz Rummel, Messi is a well-known company performing hydrofracturing measurements worldwide. And Gert Klee also supervises site activities, so he will speak as a practitioner. So the title of his presentation is Hydraulic Fracturing Stress Measurements, Theory and Practice from Engineering Projects. Gert, please, you can proceed.
Okay. Okay, can you see this? Yes.
Yes.
Okay. Good. Thanks, thanks, Philippe. As you mentioned, I'm more a practitioner than the guy dealing with theoretical aspects of this. Nevertheless, as a first speaker, I'm in the good position that I can present first the theory of hydraulic fracturing. And in the second part, I will talk about some practical aspects, equipment and application in civil engineering. As you all know, there is a large number of different stress measurement methods, which can be roughly clustered into groups. One is the observation of the rock mass behavior. For instance, the failure of a borehole, we call it breakouts, or disking as the most prominent techniques. And on the other side are techniques which are based on the disturbance of the rock mass condition by inducing strains, deformation, and crack opening. This is a group of all the relief methods. The most prominent is certainly this overcoring in boreholes. And on the other side, the second group here is the hydraulic methods, which can be subdivided into tests or two techniques. This is the classical hydraulic fracturing and the technique of hydraulic testing of pre-existing fractures. The reason why we are talking today, or why hydraulic fracturing and HDPF testing has become the most important stress testing technique, particularly in deep boreholes, is that the volume of rock we consider, the volume of rock which is involved in the test is relatively large. That means that, for instance, for the design of a tunnel, we create a fracture which has the same dimension like the tunnel itself. In comparison, for instance, to overcoring, where we consider the stresses in the order of the grain size of the rock. Good. Hydraulic fracturing as a stress testing technique was first introduced in the early 60s of the last in 1960, 62. This is one of the early papers by Fairhurst, measurement of in situ stresses with particular reference to hydraulic fracturing. I put this here because he already stated here in the early 60s that the technique has important advantages compared to other methods. And from my teacher, Fritz Rummel, I still have one of his pictures. He took during a height effect test demonstration in 1969 a granite quarry in northern Minnesota when he was working together with Professor Fairhurst here, young Professor Fairhurst. And you can see here the result of such a splitting experiment. A cubic block of granite is split in half simply by the injection of fluid. So the principle of hydraulic fracturing is rather simple, yeah? As indicated here in the left figure. Yeah? What we do is we apply fluid pressure in a borehole section, usually 1 meter, and this borehole section is isolated from the rest of the borehole by inflatable packers. Yeah? And we pressurize this test chamber to a pressure where we create a fracture. This creation of a fracture is marked in a pressure versus time diagram by a sudden pressure drop here. This is the flow rate and this is the pressure. And we continuously pump fluid into the borehole and suddenly the pressure drops here at a certain value. And yeah, this time we initiated a fracture which is on the drop is caused by the creation of new volume. We created a fracture which is usually aligned with the direction of the maximum horizontal stress that is perpendicular to the minimum horizontal stress. This during the subsequent injection, we reopen this fracture, maintain this pressure, yeah, drive the fracture away from the borehole. When the fluid injection is terminated, we observe what we call a shut-in pressure, yeah, which is a pressure to keep this fracture a little bit open. Okay, that's a principle. To understand a little bit what the background of this is, we have to consider the stress distribution around the borehole. For this, we have to consider a borehole drilled in a parallel to the z-axis in a homogeneous isotropic and elastic material. The material is subject to far-field principal stresses. S1 is larger than S3. And we have a borehole here of certain radius, and the borehole is filled with water. And it was Kirsch in 1898. This is a solution for the radial stress and for the tangential stress acting the far field of the ball. And if we consider these Kirsch equations at the borehole wall, we can derive a very simple expression here for the tangential stress. And we see here the cosinus of the point where we are along the borehole circumference. So we can show that for theta is 0 or 180 degrees, we have a minimum tangential stress, and for 90 degrees and 270 degrees, we have a maximum there. That means that at where we have the maximum, the borehole is under compression. In the versus case, the borehole can fail here and can create breakouts. And we have on the other side, reduced compression and the borehole can be tensile. That means when the borehole is pressurized, and I substituted here sigma S1 and S3 by SH min and SH max. When we pressurize the borehole, we have to overcome the stress concentration around the borehole, plus the tensile strength of the rock. This was first introduced by Hubbard and Willis in 1957, and they came up with this simple expression that the critical pressure to initiate this fracture depends only on the stress concentration around the borehole, plus the tensile strength, and we may also consider the pore pressure. In this case, the fracture will propagate the easiest path of the least resistance, and this is the direction where the tangential stress has a minimum. This is parallel to the maximum horizontal stress. Very simple expression. And for the case when we interrupt the fluid injection here to keep this fracture a little bit open, to compensate the normal stress acting here, we can use the so-called shut-in pressure as a direct measurement of the minimum horizontal stress. This is why this technique, this stress testing technique, is considered as a direct stress measurement in comparison to overcoring or other techniques where we measure deformation and back calculate stresses. But after we have created this fracture and we have drained the system, we reopen this fracture, then the strength of the rock is 0, and we get an easy expression also for the fracture reopening pressure, which is simply 3 times the minimum horizontal stress minus the maximum horizontal stress. So we can measure minimum horizontal stress directly and can calculate the maximum horizontal stress from the characteristic pressure data during the experiment. Unfortunately, the rock is in reality not as homogeneous and isotropic and elastic as described, and we often have to deal with so-called pre-existing fractures. And it was Cornet and Wallet, his co-worker Wallet in 1984, and also here in Bochum, Jörg Baumgärtner, they spent a lot of efforts to consider this particular case that we do not initiate fractures aligned with the maximum horizontal stress. They considered the case that we open pre-existing fracture which can have any orientation in space. Yeah, and in this particular case, our shut-in pressure does not represent the minimum horizontal stress anymore. It is a measure of the normal stress acting on this fracture plane. They derived an expression for the normal stress on a particular fracture. It's an equation system with 6 unknowns without all details, but you know, if you have 6 unknowns, you need at least 6 measurements of this normal stress to derive the stress tensor at depth. Good, this is a theoretical background of the 2 methods. Very briefly, in practice, we have to talk about first, when we do hydrophilic stress measurements, is how do we get the double packer unit into the borehole. There are in general two systems available. One is based on tubing, a thin tubing, which has to be connected and is usually installed in the borehole with the help of a drill rig. And on the other side, we have wireline-based system where the straddle packer unit is moved in the borehole on a cable together with a mobile windshield. I will come back to this in a minute. On the right side, just for illustration, that you certainly have to deal with different borehole diameters, different type of packers. We have packers. These have generally a capacity of about 300 bars. So the rubber here needs to be reinforced. There are different reinforcements available on the market, either nylon or Kevlar or steel net reinforcement is the available technology today. In the center is 2 packer types we developed for the special case of testing in geothermal wells, where the temperature is much higher than the rubber can withstand, which is in the order of 120. New developments say yield pivot packers which can work up to 150 degrees. But these packers here were used in geothermal wells, temperatures of about 200 degrees C, simply by expansion of the metal. The disadvantage is certainly you cannot recover this. Yeah? You cannot deflate these packers. Okay,
Gert, please, excuse me, Gert, you have 5 minutes left, please.
Yeah, okay. Back to the wireline system, I want to show you is what we here use, which is also used by other groups. We fix the tool into the borehole with a winch, and the secret of this system is that we have only one hydraulic line here, and we have a push-pull valve. We use a push-pull valve both, which permits to pressurize both the packers and the test interval only with one line. Okay, this is a photo of this system, a 2,000-meter winch unit, straddle packer unit here, and this is the coil tubing. This is in a project site in Australia. The disadvantage of the wireline hydraulic fracturing is certainly that you have a limited pull-out force, compared to when you connect the packer units on pipes. The advantage is that you can work fully independent of a drill rig and a drilling crew, that you can measure the pressure directly in the tool, that you have a very high system stiffness since you have only these thin coil tubing lines. So you have a small volume. Okay, these are some photographs of more mobile system used in geotechnical applications. Here is a 500-meter unit. This is a typical in-mine unit with a hand winch. The equipment needs to be in geotechnics needs to be mobile, since the access to the borehole sites is very difficult. So we need sometimes helicopters, sometimes we have to move the equipment with the help of some animals. This is a photo taken, I guess, in Patagonia, in Chile. As I mentioned at the beginning, the fracture will be aligned with the direction of the maximum horizontal stress. So we need to determine the fracture orientation. There are different techniques available to do this. The most simplest way is the impression packer. This is a single packer with a soft rubber skin, which is pressurized against the borehole wall. And you can see the fracture trace on these soft rubber skin, here marked with chalk. So the tool is an orientation device, which gives you the orientation of a certain reference mark with respect to the orientation of the fracture. You can also use BHTV logging, acoustic borehole televiewer logging, an image before and after fracturing. You can see the fracture here, and steeply inclined fracture. Or even a formation microscanner. It's a product of Schlumberger, where you measure the resistivity of the borehole wall. And you can see here in this example the fracture trace. Okay, very briefly, I'd like to show you one application. This was generally we have the problem that we, as a private company, we are not allowed to show data, but here we got the permission from a hydropower project in Laos. We showed this 2016 on the Rock Mechanics Symposium in Bali. The project is located in Laos, in the south of Laos, a plateau here, which has an elevation, different elevation of about 600 meters. And the project consists of two reservoirs connected by a transfer conduit, headrace tunnel, nearly 500-meter deep shaft with a high-pressure tunnel. For the design of the lining in this shaft and the high-pressure tunnel, stress measurements are of particular importance. Just for your information, the geology there is Upper Cretaceous or Upper Jurassic Cretaceous rock, and with an unconformity to the lower or middle Jurassic rocks, mainly siltstones and sandstones. Here's the location of the two boreholes we tested. The site, okay, I will do this very briefly. 11 tests in the deep borehole, 9 tests in the shallower borehole. And the results clearly show, very consistent data here in the minimum and maximum horizontal stress in the both boreholes. The deeper part, we can see higher stresses, and we see a transition from these low level to the higher level across the border between the upper and lower Jurassic rocks. When we compare these data, the minimum horizontal stress with the pressure value in the tunnel and in the shaft, we see that in the shallower borehole, in the middle of the high pressure tunnel, the minimum horizontal stress is in the same order than the water pressure in the tunnel. So this cost, we need a lining here, but in comparison to the initial design of the project, where about 2,080-meter lining was necessary along the shaft and the high pressure tunnel, we could reduce this to 1,250 meters. So we shared about 40% of the steel lining, which contributed to save a considerable amount of money. Yeah. So hydraulic fracturing is an efficient method. I will come to the end now for determining the two-dimensional 2D stress field, yeah, particularly at great depths. There is a limitation that tests should be conducted in vertical to subvertical borehole. We can directly measure the minimum horizontal stress with a good accuracy of plus minus 5%. Maximum horizontal stress is certainly not as precise as this test, but still within 10 to 20%. The drawback is certainly that we require for hydraulic fracturing test section without fractures. Yeah, HDPF relies on has less limitation and relies only on 4 parameters. And from my 30 years experience, when I'm asked by clients, what shall we do? I always recommend to combine hydraulic fracturing with HDPF tests, and this has to be cost efficient. And for this, a wireline system is an appropriate tool. Thank you.
Thank you, Gert.
Sorry for being 4 minutes longer.
Thank you, Gert, for this very, very interesting presentation. We will have many questions to ask you, but right now we're going to the second speaker. So our second speaker is Arne Marius Rijn. Arne Marius Rijn is a physicist. He worked in Statoil, a major oil and gas company, and is currently working with Sintef in Norway. His activities cover rock mechanics and oil and gas related activities, of course, such as water injection, sand prediction, and of course, in situ stress measurements in wells. The title of his presentation is Minimum Stress Measurements in Deep Offshore Wells. You can proceed, Arne.
Thank you very much. I'm going to focus on one of the methods that's used offshore, but is kind of the workhorse and what we think is the most reliable. And the outline of my talk is, I need to move the mouse, is since in principle we are doing exactly the same thing. I will not go into details. I will try to highlight what's different in the offshore environment in a deep petroleum well as compared to in hard rock. And the main difference is, of course, that we work with a very, very large volume, and that we normally do this kind of test with the mud that's actually used for drilling. So it's a viscous, it has particles and so on, and which means that the decay in tight formation is very small. This has led us to the use of flow back test, in which you don't only shut in, but you flow back the fluid back into the well to see the response when you do that. And that has led us to interpret this in a very simple way in what we call the system stiffness concept. And I will show a few field examples oral from published data available in the public domain. So in simple view, what you do when you do a casing shoot test, which is typically done at, say, 1 kilometer to 2 kilometer to 3 kilometers depth, is that you drill a section of your borehole, and then you run an intermediate casing to seal off the borehole and stabilize the borehole. You cement the casing in place, and then you drill out the casing, and you drill a few meters of new formation. Typically, the guidance is that you should drill, say, 3 meters of new formations before you do the test. So as kind of a big overview of what you're doing, a principal sketch is that then you have here a well, you are creating a fracture, and you have the possibility to flow back. And then what we do is we will pump typically 1 to 3 cubic meters of fluid or mud at the rate of 100 liters per minute. I guess both numbers are much bigger than you are used to. And then a big difference, and we see complicated interpretation, is that we have a wellbore, an open wellbore with the size of typically 100 cubic meters. And we create a fracture, which is maybe 5, 10, 20 meters in length, and typically 1 centimeter in width, and a volume of typically 500 to 1,000 to 1,500 liters. And then after pumping, we flow back, and you get back some of your mud back. Sometimes you get very little back. Sometimes you get even most of the mud back, and the flowback time is usually a few minutes. And we found that this flowback phase is very important to get good interpretations. So in the next slide, and of course, the question is how much do you lose, and that varies a lot from case to case. Here is a plot, kind of the classic picture from the petroleum industry of an extended Likov test. It's from a paper by Shell people from Garnstone and others back in '93, and you have here a typical pressure response as a function of time. Yellow is while you pump, while white is after you have shut in. And in this figure, we have highlighted what they call the Likov pressure, which may or may not be there, and essentially is not very well related to the stress. You have a fracture breakdown pressure, where you kind of create the fracture and propagate the fracture into the rock, kind of break down the tensile strength, as was explained by the previous speaker. And then you pump, and you have what we call a fracture propagation pressure, which is often reasonably constant, and we pump until we have pumped sufficient amount of fluid into the formation. Then the shut-in, after shut-in, you have the instantaneous shut-in pressures where frictions are gone, and then after you shut in, you will see that the pressure falls off depending on the properties of your formation and your mud. And the traditional interpretation has been to take fit straight lines to this behavior after the instantaneous shut-in, and interpret this crossing more or less as the minimum stress. So I'll show you here the results from an extended Likov test with flowback published about 20 years ago. We have in yellow here the pumping phase, we have in white the shut-in phase, and we have in pink here the flowback phase. And the question is, where is the in situ stress here? And what we found is that the in situ stress is not at the instantaneous shut-in pressure, and it is not where the pressure level off, but it's somewhere here in the structure that you see in the flowback phase. So with the system we have relatively tight formation, not much fractures, the mud that would seal the fractures. It's very important to do the flowback phase, because if you didn't do it, you would probably estimate it to high stress. The way we try to understand it is in a very, very simple picture. We look at the stiffness of the system as a whole. And as you remember, we have this vast volume in the wellbore that we pressurize. And so when you pump in, you get a pressure versus volume behavior that is given essentially by the compressibility of the fluid that you use, oil-based or water-based mud, and the volume of the well. And of course, there's some small contributions from expanding the casing has increased the pressure, and from expanding the rat hole below the casing, but these are normally very small. So you can essentially compute the slope that you expect from the properties of your mud and your knowledge on how big this volume is. And that is an important quality control. If the slope is not the right one, you have some leakage somewhere in the system that you need to address before going on further. Then we looked at fracture closing, and there's a paper here by Hayashi and Heimsen back in 1991, which has a simple picture of how the fracture closes. And what they say is that closing of fracture is essentially a two-stage process. It's going to be hinge-like in the initial phases, and it will only start to diminish in length in the final closing phase. And then if you look at the stiffness of an ellipsoidal fracture, which is given essentially by the modulus of the rock and the diameter or the radius of the fracture to the third power, we see that it is independent of the fracture width. And that means that during this phase where you have hinge-like closing, the stiffness of the fracture is essentially constant. It will only start to get smaller when it's getting very close to closing. So then we can look at the total system stiffness. We have the wellbore stiffness from compressing the fluid in the wellbore. We can easily compute that with a fair approximation. And the fracture stiffness, since it was dependent on this R to the power 3, it depends on the fracture size, and that means that you can control the fracture stiffness by how much you pump. And of course, the total stiffness is found by combining the compliances, the inverse stiffnesses. And you see that if you have properly designed your fracture, if you made a big enough fracture, you'll see a change in the compliance or stiffness as the fracture closes. So if you now plot the pumping phase together with the flowback phase, it should, in an idealist situation, look like this. You have pumping, you have the stiffness in pumping, and in the flowback, unless you are leak of much deformation, which is typically not the case in our offshore wells, you should see essentially the same stiffness during pumping and during shutting, but you should see a lower stiffness when the fracture is open. So in this kind of cartoon, you go from one stiffness with an open fracture and back to the boreal stiffness after the fracture has closed. And that gives you a fairly good estimate of what is the in situ stress. It's somewhere near this kink here.
Arno, you have 5 minutes left.
Okay, thank you. So I'll move on to show some field data. And here for an offshore well published in 2006, and what I plot in here is the surface pressures versus time for the entire test. Yellow is the pumping phase, the white or light is the shut-in phase in cycle 1, and red is the flowback phase. And you can see in this particular test, there is no clear leak-off point, at least not in any region where you expect the stress to be. There's some structure up here, but that might be due to a change in pumping rate and so on. So we have a very straight line until the formation breaks down. We always do a second cycle, and this is from the second cycle. And what we typically do on the second cycle is to leave out the shutting phase, but we go straight to a flowback phase. And you see that here also during pumping, you now have an open, create a fracture, and you don't have this big breakdown pressure. You're kind of opening the fracture that you made in the first cycle. From the flowback phase here, we can estimate what we think is the in situ stress level. And you see that by chance in the first cycle, we essentially change phases from shut-in to flowback phase exactly at the more or less exactly at the in situ stress level, and that's why we see very little in the flowback phase in the first cycle. However, the second cycle has some very clear structure that allows us to estimate the in situ stress. We can plot this in another way, not very plot pressure versus volume, and what we choose to do is to plot the volume remain in the well. So when you flow back, you draw the curve backwards. As before, yellow is pumping, cycle 1, cycle 2. White is the shut-in phase of cycle 1. There was no shut-in phase in cycle 2. And the red is then the flowback phases. And of course, only cycle 2 in this case has a very distinct behavior during the flowback. So I can fit straight line now to this. First I need to see that this way of plotting it gives us a direct picture of how much do you lose in each cycle. So you can see that we lost much more fluid in the first cycle than in the second cycle. And then to find the stress level, I'll fit the straight line during the hinge-like closing of the fracture and a straight line to where we have the closed fracture, and you only see the well response. And you can see that we get an intersect here, which is close to where I draw this estimated in situ stress line. Then I can look at this slope of that line that I put around. I just shift it now. I don't fit the new line to the other curves. I just shift it, and you see that both for the final shut-in phase or flowback phase of the first cycle and for the pumping phase, we have essentially the same slope. This is a kind of an ideal field result. Not all field results are this perfect, but this is kind of exactly in line with the very simple theory that I sketched in terms of the system stiffness. I can also move this open fracture line up to the pumping phase for the second cycle, and you can see that again. You see that it's essentially the same site fracture we're pumping into. The slopes are the same. So you have an open fracture here, and has not much changed much from pumping to flowback. So it's kind of a consistent picture that we have of what happened during the flowback phase, and that means that we trust these results to be correct. So I guess I need to try to conclude. And our conclusion has been that in the offshore environment, because of these special things with this big volume, you don't have downhole packers. The flowback test is by far the preferred test, and to get good data, you need to do a flowback test. We also saw that in one of my first slides, that seems to give a lower stress estimate than if you were to try to estimate it from the shut-in phase, just because the formation is so tight that you don't leak off from your fracture. You essentially don't close your fractures. And of course, in the offshore environment, it is a big safety effect to know the stress level. And if you miss by maybe 20 bar, it can make a big difference. So all in all, we believe this flowback test, it gives a very robust method, although essentially the same as done in harder rock. The small changes that we made to it makes for a much better test in the offshore environment. Thank you.
Thank you very much, Arne, for this very interesting presentation, and especially for emphasizing the differences between oil and gas and hard rock environment. Before going the possibility to the audience to ask question, does one of the two speakers have question to the other or comments? No?
I want to comment.
Yeah.
It is always, thanks for the presentation, Arne. It is always impressive when I compare using our system. We have a volume, say 1,000 meters is a volume of 50 liters. Yeah. Your volume is 1,000 meter borehole with several hundred of cubic meters plus the open hole borehole section plus the fracture you create, which is probably rather large. Yeah, we inject during one of the experiment I showed. Yeah, typically the total volume we inject in low permeable rock is in the order of 10 to 20 liter during such an experiment. Yeah, and that's the reason why we are talking probably from completely different things. Yeah, it sounds similar, but the reality is completely different.
Yeah. I didn't go into it because I didn't think I had enough time. But of course, there's other methods used in the oil industry as well, and we have some Y-line tools that goes down on a Y-line with the dual packers, which looks much more like what what you do. So Schlumberger has this kind of tool, for instance.
Yeah.
So and then the volumes are much smaller, and you don't have this problem with the big volume from the open borehole. But still, the workhorse, what we do is this casing tube test, because every casing tube needs to test it anyway, and you get the stress by extending a test that you would do anyway by half an hour to one hour. So it's the cheapest way, and also probably the most robust way of getting stress data.
Mm-hmm. Your comment is right, Gert. This is different world. Sure. Yes. Now it's time for the audience to ask questions. Could we stop the screen sharing? Okay, yes. So if someone wants to ask a question, he can. I have seen a lot of chat discussions. Yes. If you want to ask a question, please, you tell your name and you ask then your question.
I guess there is a question in the chat by
in
Charlie.
the chat, we do have things for you, Gert. Yes.
Yeah, I tried to raise my hand, but I could not find the function.
Okay.
Yeah, Gert, you get my question.
So the first one is: could leakage be a problem in shallow positions with HTPF?
What do you mean with leakage?
Yeah, leakage. If the fracture, the pre-existing fracture is open, when you pump the water will disappear, will leak. Is that a problem?
You mean the fracture is permeable? Yeah.
Yeah. Each system has a limitation. Yeah. For instance, we use this coil tubing. I mentioned this has an internal diameter of let's say 8 millimeters. Yeah, and you cannot inject 100 liters per minute through such a system. Yeah. So we use, for instance, a pump 10 liters per minute. Yeah. So if the fracture is, let's say, conductivity of 10 to the minus 5 meters per second or something like this, yeah, we will not observe any pressure build-up with these 10 liters per minute. Yeah. So then the test, it is also an information, but the test cannot be used for the stress estimation. Yeah. So the limitation is certainly what we can inject into this permeable fracture. Yeah. The second question, do you prefer hydrofrac or HDPF? When I was together with François Cornet and Fritz Rummel, we always tried to do both in a boat. To create a fracture which gives you from the physics the direction of the stresses with a certain reliability. And we also try to open pre-existing fracture to constrain the maximum horizontal stress.
Yeah, more directly, Philip, excuse me. Yeah. More directly, which do you believe better? These two.
There is no difference. There is no difference. I believe to my data. Yeah. The question is, can you precisely determine the shut-in pressure, or the jacking pressure, and the corresponding fracture orientation? Yeah, this is the point. Yeah, is not what I believe.
Okay, thank you.
In addition to that question, Gert, in hydrofracturing, in standard hydrofracturing, there is an assumption that one stress component is vertical. Do you consider this assumption as valid as regard to your comparisons between HF and HTPF?
Sorry, maybe I missed your question. You mean the vertical stress is a principal stress?
Yes.
Yes, this is, I mean, in 99% of all cases where we do the stress measurements, the vertical stress is a principal stress. Okay, you can investigate this by flag modeling, 2-dimensional or 3-dimensional. The influence of the topography is when you are, let's say, outside the Alps,
Yes, of course.
Yeah, you can neglect this.
Okay, okay, very interesting.
Yeah.
Thank you.
And I guess it is also published in many papers that the vertical stress is it corresponds to the weight of the overburden for a given density.
Yes. We have a question from Luis Lamas. Are HF or HTPF tests applicable for relatively shallow zones, say 200 to 300 meters? What would be the minimum depth?
There is, I mean, we have conducted in Hong Kong tests at 20-meter depths, yeah, where we opened pre-existing fracture and also initiated new fractures. There is no depth limitation to the top and also down. We can go as much as the equipment can go. Yeah.
Arne, in the oil and gas industry, how deep do you test?
Could be at least 2.5 to 3 kilometers. I guess we have some tests that's deeper than that as well.
Okay, thank you. We have a question, or maybe more a comment from Nick Barton. Do you want to talk, Nick? It will be easier.
Yeah, sure. You can hear me?
Yes.
Okay. So yeah, I'm not the only older guy in the room, so to speak. So back in the 1980s, when I was a few years with Terratech in Salt Lake City, I was responsible for doing hydraulic fracturing at a pump storage site, again, rather like one of the examples given in the nice lectures, to find out where how long along the pressure tunnel one would need to take heavy steel reinforcements. And we also managed to save some money. And the interesting thing was that the 4 or 5 boreholes we had that were vertical, they went through deeply dipping interbedded sediments, sandstone, siltstone, mudstone. And consistently in these boreholes, so probably 20 tests, the minimum, or the K0, the minimum stress divided by the vertical stress calculated, was highest for the higher modulus sandstone, about 1.2, I think, and then in the siltstone, 0.9, in the mudstone, 0.6, and so on. So it looked like the modulus and or the shear strength was playing a role there. Later, I got involved in doing sort of rather larger scale, massive hydraulic fracturing studies for some oil companies, also for Shell, actually, over in Holland, and also in Albushel in the early 80s. And there, it was interesting that one was again going through interbedded sandstone shale, or let's say the equivalent of compacted mudstone. And the minimum stress in the cap rock, which was designed to be the shale or the mudstone, was much higher. Yeah. So in other words, at 3 kilometers depth, the mudstone or shale, it didn't tolerate a big stress difference, because different sigma 1, sigma 2, sigma 3 means that you can tolerate stress difference, or you have some shear stress. So the shale in the cap rock was a high K0 as desired to contain massive hydraulic fractures, whereas a few hundred meters depth, similar rocks, they had low K0 according to the differential strengths. Yeah, I don't know if anyone has noticed that. I haven't seen it reported, but one cannot read all the literature, of course.
Who wants to answer?
I interpreted the differences as possibly different unloading moduli, because wherever one is at the surface, there may have been erosion, and you're on probably an unloading curve as observed today. And maybe these different sandstone, siltstone, mudstone, they had relatively different moduli and or shear strength. So they could tolerate stress difference at shallow depth, but the same rocks cannot tolerate stress difference at a few kilometers depth. Therefore, you have nice cap rocks. So it's a very fundamental mechanism why we can have oil and gas, yeah, that hasn't leaked to the surface.
Any comment, Gert?
I'm not so much involved in this investigation in cap rock, in oil and gas. For the pumps, for the interbedded sedimentary rocks, the one example, I mean, what I can say is often I'm asked, we have horizontally layered rock, and can you really create a vertical fracture? And in the example I showed from the formation microscanner log, this was a log in Switzerland. It's not very deep, 400 meters from a nuclear waste deposit site. Usually the fracture do not care about the layering of the rock. Something what we often observe.
Any additional comment?
These were vertical fractures. I mean, we used impression packers to see vertical fractures, for the perpendicular to the minimum stress, parallel to the major horizontal stress.
Maybe one small comment, and that is from the data I showed. There, in a tight zone, you need to do a flowback test. So in that case, if you do a test in a sandstone, a traditional shut-in test might do it, but it might overestimate your stress in the shale. So I don't know whether that is the case, but it could be a mechanism.
It could be
explaining that you report higher stresses in the shale than in the sands, because in the shales, in deep offshore, if you did it all the way, you probably didn't close the fracture.
But I mean, if you didn't have a minimum stress in the shale higher than the sandstone, we wouldn't have any oil reservoirs in those sediments.
No, I'm not.
So it's rather an important mechanism,
It's just one factor you need to take into account in the interpretation.
Okay, we have another question.
Philippe?
Yes?
Angelica raised her hand for a long time ago. Let her a question.
I'm sorry, but I cannot.
Angelica.
I cannot.
No problem.
Okay, please.
Okay, thank you very much. So it's Angelica speaking, Angelica from EPFL Switzerland. So first of all, thanks to both speakers for the interesting talk and to the organization. So I have a first question to Gerd Klieb. So I saw in your last slide some numbers about accuracy. So I was wondering how much are you confident about this value of accuracy that you were providing, and if you remember from which comparison they are coming, because I guess there should be a comparison between the estimation and some known values that on which we are believing in. So this is the first question, and then maybe I ask the second and I leave them to reply, or I just wait the answer first.
Okay, these 5%, originates from the following observation. Once you have created a fracture, you extend this fracture step by step with the stiff system we have. You can do this, You extend the fracture step by step in length, and from a certain, let's say, usually after the second injection cycle, you will observe that the shut-in pressure remains more or less constant on a certain level. It drops maybe by 1 bar. So you measure 100, 99, 99, 98. So to be confident, you can say, okay, I can make a mean value of these 5 value, or I take the final one. But usually you can repeat your experiment, many times. And the pressure, it is like a memory. It is a balance, and once you balance this fracture, properly, you get a very consistent values. That's why we think the minimum horizontal stress is measured by the shut-in pressure within an accuracy of maybe it is 10% or 5%, but it is a value which you can reproduce many times.
Okay, so Okay, many thanks. So basically the reproduction and so the accuracy that you are talking about is like a consistency of result of multiple results that you are getting from the same. It is the case. Okay, many thanks.
Yeah, and the error in the SH max estimation is certainly, I mean, 20%. Okay. You know, hydraulic fracturing is used since 70 years now as stress testing technique, but still the definition of the fracture reopening pressure is a problem, to be honest, So where is the point where the fracture really opens? There are a couple of publications concerning the technique you have to apply. You have to plot pressure versus stiffness or whatever, or you have to use a very high system stiffness. Is a publication by Keith Evans, who investigated the influence of the stiffness on the value you determine. So the refract pressure is difficult to determine, and that's the reason why we have problems to say what's the maximum horizontal stresses. And there's also a question, is it necessary here from Philippe Vaskou, is it necessary to have a previous estimation of the tensile strength of the jointed rock to derive, So you can neglect the refract pressure and you can measure the tensile strength on the rock samples in laboratory. There are people doing this. But we believe it is more accurate to use the field value because it is a test on the same sample size. When you use tensile strength, you have several techniques. You can use Brazilian tensile strength, or you measure tensile strength in an hydraulic experiment in lab. This is the same problem, more or less.
There is a question from Eva Kami. What is the highest stress ever measured?
It's a good question.
Yes.
I mean, the deepest test I know, is the 9-kilometer hydraulic injection experiment, 9.1 kilometer depth in the German continental deep drilling program. In 2000 and a little bit. Mark Sobak was there and all the other guys. This was probably the deepest stress measurement ever done, and probably also the derived results are the highest stresses ever observed, because it is on the deepest, on the greatest depth.
Okay, there is also an interesting question to Gert. In HTPF, when the fracture in borehole connects a second joint, for example, cross joints, will the situation may impact the accuracy of the method, and by how much?
This is certainly the versus case we can have. That we believe what we see on the borehole wall is the fracture we simulate far away from the borehole. If this borehole is connected to cross joint or something, maybe perpendicular to this, our assumption that the shut-in pressure corresponds to the fracture we observe at the borehole wall is not valid anymore. This is the versus case. And certainly it is also the limitation of this technique.
But you can easily detect the phenomenon?
You should, because the shut-in pressures from an early stage of the experiment and from a later stage of the experiment should differ.
Should be rather different.
And since water always flow into the path of the least resistance, it is hard to understand why, when water flows this direction, why it should go this direction be against a higher stress. Usually it should continue in the same direction.
Okay. A very interesting question from Nick about shearing. To Gert and others who have done HTPF, have you sometimes to scrap data due to suspected shearing of the inclined joint? Or reformulate, you calculate the normal stress to a fracture, but can you evidence some shear stress or deformation?
Hard to say. To be honest, this is hard to say.
Okay, that will be the answer. Leandro, to determine the stress field in hard rock from standard HF test, do you resort to the tensile strength based on Hubbert and Willis standard approach, or to fracture mechanics approaches as developed by Romain some time ago? You know this. You know this very well.
Yes,
of course.
Yeah. Yes and no. Yeah, yes. We use the standard Hubbert and Willis procedure, but we also, when we got the chance to do this, we take rock samples and do the fracture mechanics laboratory tests to estimate the tensile strength also with this fracture mechanics approach suggested by Rommel in 1989. Yeah. Yeah, but somebody must also pay a little bit for this.
Yes, of course. You mean the client, the final client, of course.
Yeah. But if possible, we try to do this because it is an interesting approach.
Okay, another question from Guillaume Modeste. During HTPF campaigns, how many levels are you testing along the boreholes?
Yeah.
And what do you observe?
Yeah, as I said, you need, practically, you need a minimum of 6 tests to solve this equation system with 6 unknowns. Usually we are asked by clients, or often we are asked by clients, hey, can you do 3 hydraulic fracturing tests or so on? And I always tell them the same. The costs for these tests are not the test itself, it is a mobilization of equipment and personnel.
Yes.
Once we are on site, it makes more or less no difference whether we do 3 tests or we do 10 tests. Because you can do with a wireline system in a borehole of 1,000 meters in one day at least 10 hydrofrac or HTPF tests. Yeah. And then you have to do certainly more impression packer tests or logging work. Yeah. But we try to do as much as possible tests. Yeah? Because we do not know during the conduction of the test whether we will have a classical hydrofrac or a pre-existing fracture. Yeah?
Yes. Okay. We have no more question. We are more or less at the end. Arne, I have a question to ask you. What is the difficulty of calculating in-situ stresses, taking into account the mud instead of pure water and the permeability in a sandstone?
Yeah, it's to get the smallest test is fairly straightforward with the flow back method, irrespective of the permeability. The biggest stress we really don't attempt much in the deep offshore well, because there's so many things that could go wrong.
Yeah.
Sometimes you done something to your borehole before you try to do a test that made a small fracture, and you simply can't use the linear elastic approach. And of course, these are also weak, relatively soft rocks. So that would mean that the linear elastic approach does not work. So we're very skeptical to trying to get the major stress in the offshore wells.
Okay. Well, two last questions. One from Nick. In a paper 1986, I sketched without knowing the answer, shearing in stage of H-frac opening. Do you suspect sometimes?
I sketched without knowing the answer, shearing in stage of hydrofrac.
We're still in the problem about shearing, of course. Of course.
I mean, to create shearing on the fracture, Nick, you need a fracture which is approximately at least 30 degrees off the direction of the maximum horizontal stress. Yeah?
No, actually, I was not assuming a fracture in the second question. I was assuming intact rock. If you had very high stress anisotropy, will you automatically get the sort of weakest link, which presumably is breaking the tensile strength, could you have a shearing or not? I don't know the answer.
I think no.
Oh, okay.
Okay. Well, you stop the the question now because it will be too late. But
Charlie have raised his hand. I think Charlie.
Yes, Charlie.
Okay.
Okay, I have sent in the message, but this is a question to Arne. So I wonder how far the fracture could be propagated, from the borehole during the testing.
Typically 10 meters.
10 meters.
More than 5, less than 30.
Is that
Depends
possible?
on how much you pump.
Is that possible? The fracture direction is changed.
Yes. So we feel most confident when you do this in near vertical wells, but we also have good results in inclined wells and some bad results in vertical wells. So
that means the measured stress will be changed too if the direction of the fracture is changed.
Yeah, but what we think is it changes relatively fast. If you have your borehole is unfortunately aligned with respect to the stress, it should change within a meter or two, and then you have most of the fracture seeing the far field stress. But of course, there's a risk here that you kind of stop the communication near the wellbore at the highest stress, and you miss the correct stress. That's definitely a possibility.
Do you have a requirement for the minimum fracture depth?
The requirement is that you should make it as big as is necessary to see a contrast between the wellbore stiffness and the combined fracture and wellbore stiffnesses. So if you create a too small fracture, you will not have this difference, and the flowback test will not work.
No.
Okay.
Interesting. Thank you.
Okay. Arne, the last question. Do you have specific procedures to assess the quality of the results?
Yes, you saw in my cartoons there was a kind of a fixed thing between the two lines, which is not what you saw in the real data. In the real data, there is a smooth transition from the one slope to the other, and we are not exactly sure we're in that the region you should put the stress. So there's an intrinsic inherent uncertainty related to this shape of this curve, which adds at least to 5, 10, 20 bars.
Okay.
And there's other questions up here which says that you have only one way, and the answer to that the third from below here. And that answers to that is we have in some cases had successful tests where we have found the zone where there's some leak off, so that we can compare directly a shut-in test to a flowback test, and they seem to be very close to each other. So under conditions which are appropriate for a shut-in test, they give the same as the flowback test.
Okay, thank you. Well, I think we are at the end. I would like to thank very much our two speakers, Gert Klee and Arne Marius Rehn. Thank you very much for these very interesting and technical presentations. Thanks also to the audience and for all these questions coming from the audience. Leandro, would you add a few words of general comments?
I have some words, Leandro.
Yeah. Okay, yeah, I mean, please, Resat, yeah.
On behalf of the ISRM board, first of all, I would like to convey to my sincere thanks and the congratulations to our colleagues, Charlie Li, who is the first recommendation of this organization of this debate, and other colleagues, Leandro Alejano and Philippe Vaskou, who acted as the organization committee of this very successful initiative, and also our two speakers for their very interesting presentations and the information they shared with us, and all colleagues who participated to this meeting. And I believe that this series of debates will be very useful and interesting, and also helpful for the collection of opinions and suggestions from our community. And I expect that next year or coming years, the number of participants to these debates will increase. Thank you very much.
Okay, thank you, Resad. I think we have had more or less 50 to 60 attendants.
61.
Well, yeah, and I don't know, but also, I mean, probably some people have followed this in the YouTube channel. So I want to thank also everyone for their presence here today, and the participants and speakers, and also ask you for your, maybe if you have any ideas of possible debates between two informed persons, that would be nice to have it. So, oh, sorry. So with that, I think we can close the meeting. Philippe, if you want to make the official closure.
Okay, so well, thank you very much for attending. We do hope to see you next year for another debate for this ISRM Europe series of debate. Okay, thank you very much. Goodbye.
Bye-bye.
Bye-bye.
Thank you, Gerd. Anna. Thanks.